In the YouTube video titled Lecture 7, Introduction to Galois Fields for the AES by Christof Paar, Professor Christof Paar provides an introductory lecture on the concept of Galois Fields, a fundamental mathematical construct essential for comprehending the Advanced Encryption Standard, AES. The lecture begins with an overview of the global impact and importance of AES as an encryption standard, highlighting its widespread adoption and significance. Paar then underscores the crucial role of Galois fields in understanding AES, emphasizing that they are finite fields, characterized by their finite number of elements. The video proceeds to elucidate the properties and characteristics of Galois fields, including the arithmetic operations of addition, multiplication, and inversion, which are performed modulo a chosen prime number. He further emphasizes the importance of prime numbers in defining the structure and size of a Galois field, noting that each prime number uniquely determines the number of elements within the field. The lecture then delves into the construction of larger Galois fields through the process of field extension. Paar explains how field extensions are created by combining elements from an existing, smaller field with a new, irreducible polynomial, thereby expanding the field's structure and properties. The video incorporates several illustrative examples to solidify the understanding of Galois fields and their arithmetic operations. These examples demonstrate the mechanics of addition, multiplication, and inversion within these fields, emphasizing the use of modular arithmetic. The lecture also touches upon the use of polynomial representation in describing the elements of Galois fields, further clarifying their algebraic nature. The video concludes by reiterating the indispensable role of Galois fields in cryptography, particularly in the context of AES. Paar emphasizes that a solid understanding of Galois fields enables a deeper comprehension of the mathematical underpinnings of AES and its mechanism for secure encryption. From 0 minutes to 5 minutes of the video, Christof Paar begins by contextualizing the significance of the Advanced Encryption Standard AES within the broader landscape of cryptography. He underscores the pivotal role of AES in the modern era, emphasizing its widespread adoption and its status as a robust successor to the Data Encryption Standard, DES. He then introduces the fundamental mathematical concept of Galois fields, emphasizing their criticality in comprehending the inner workings of AES. Paar highlights the distinctiveness of Galois fields, contrasting them with traditional mathematical fields and illuminating their unique characteristics. He then delves into the core definition of these fields, emphasizing their prominence within the discipline of discrete mathematics. Paar elucidates the defining properties of Galois fields, notably their finite nature and the presence of both addition and multiplication operations. He provides a concrete example, showcasing a Galois field consisting of 4 elements, 0, 1, 2, 3, and illustrates how operations within these fields diverge from conventional arithmetic operations. Paar emphasizes that while addition in this field adheres to expected behavior, multiplication is carried out modulo 4, entailing the reduction of any result exceeding 3 by subtracting multiples of 4 until a number between 0 and 3 is achieved. He then elaborates on the concept of prime fields, a specific category of Galois fields where the element count is a prime number. For instance, the field containing 5 elements, 0, 1, 2, 3, 4, constitutes a prime field. Paar reiterates the importance of prime fields in the context of AES and introduces the concept of field extensions, a mechanism that enables the construction of larger fields from smaller ones. As an example, he demonstrates the process of constructing a field with 16 elements by extending the prime field with 4 elements, 0, 1, 2, 3. This extension process entails the introduction of a novel element, represented as x, into the existing field, followed by the definition of its multiplication rules. Paar concludes this introductory section by highlighting the central role of Galois fields in the AES algorithm. He posits that these fields provide the foundation for all the operations executed during the encryption process, including the substitution and mixing steps. He underscores that a comprehensive understanding of Galois fields is indispensable for gaining a thorough grasp of the security and efficiency underpinning the AES algorithm. From 5 minutes to 10 minutes of the video, Christof Paar introduces the concept of Galois fields, a fundamental algebraic structure with profound implications for the Advanced Encryption Standard, AES. He underscores the significance of Galois fields in comprehending the intricate workings of AES, paralleling the importance of prime numbers in other mathematical domains. Paar elucidates that a Galois field constitutes a finite set of elements, characterized by well-defined operations for addition and multiplication. To illustrate this, he presents a simple Galois field comprised of 4 elements: 0, 1, 2, 3. He proceeds to elaborate on these operations, emphasizing that addition is carried out modulo 4, meaning that the result of any addition is the remainder obtained upon division by 4. For instance, 2 plus 3 is congruent to 1 modulo 4. The video then delves into the multiplicative operation, also executed modulo 4. Using the example of 2 by 3 congruent to 2 modulo 4, Paar accentuates the need for a thorough understanding of these specific operations within the context of Galois fields. He subsequently explores the notion of field extension, emphasizing that it entails the augmentation of the original set with additional elements. This extension proves crucial in constructing larger Galois fields, indispensable for more intricate encryption schemes. Paar underscores the pivotal role of these extensions in the development of robust encryption algorithms, highlighting their contribution to safeguarding digital information. From 10 minutes to 15 minutes of the video, the speaker delves into the concept of prime fields, which are fundamental to comprehending the Advanced Encryption Standard AES. They introduce the mathematical concept of a group, emphasizing that a group is simply a set of elements with specific operations defined on them. The speaker then elaborates on the significance of prime fields being finite, meaning they possess a finite number of elements. This finiteness property facilitates efficient computations within the field. For instance, the speaker emphasizes the importance of the prime number 256 in cryptography, as it aligns with the byte size of 8 bits prevalent in modern computing systems. They explain how 256 elements can be effectively represented using a single byte. Finally, the speaker illustrates the execution of operations such as addition and multiplication within prime fields, underscoring the concept of modular arithmetic. Modular arithmetic involves reducing results modulo a specific prime number. From 15 minutes to 20 minutes of the video, the speaker delves into the realm of prime numbers and their paramount role in modern cryptography. He elucidates that prime numbers serve as the bedrock of encryption algorithms, owing to their inherent difficulty in factorization, thereby rendering code-breaking efforts by malicious actors exceedingly arduous. The speaker then transitions to the concept of extending prime fields, emphasizing that this process essentially entails expanding the set of numerical values employed in cryptographic operations. Utilizing the prime number 11 as a concrete illustration, he demonstrates how the prime field can be augmented by the inclusion of additional elements, resulting in a more expansive prime field. The speaker unequivocally asserts that prime fields are an indispensable component of cryptography, finding frequent application in algorithms such as the Advanced Encryption Standard, AES. He proceeds to explicate that various operations, including addition, subtraction, and multiplication, can be conducted within these fields, underpinning the functionality of cryptographic algorithms. The speaker provides a practical demonstration of multiplication within a prime field, specifically illustrating the multiplication of 4 and 5 within the prime field of 11. The product, he emphasizes, is 2, achieved by executing the standard multiplication and subsequently obtaining the remainder after dividing by 11. The speaker underscores that extended prime fields, such as the one derived from the prime number 11, offer a significantly larger pool of elements for cryptographic operations, yielding enhanced flexibility and security. He emphasizes that a comprehensive understanding of prime fields is fundamental to comprehending the principles of contemporary cryptography and the intricate workings of algorithms such as AES. From 20 minutes to 25 minutes of the video, the speaker delves into the concept of prime numbers, emphasizing their fundamental role in the construction and comprehension of finite fields. The speaker employs a pedagogical approach, illustrating the concept of modular arithmetic using the prime number 11 as a concrete example. They explain that the set of residues modulo 11, consisting of numbers from 0 to 10, forms a closed system under the operations of addition and multiplication, with results represented as remainders after division by 11. The speaker then connects the concept of prime numbers to the realm of Galois fields, elucidating that prime numbers serve as the foundation for constructing these fields. This relationship, they posit, is paramount in understanding the principles of cryptography. The speaker concludes this segment by highlighting that the order of a Galois field is directly determined by a prime number, underscoring the intrinsic link between the field size and the prime number used in its construction. From 25 minutes to 30 minutes of the video, Christof Paar delves into the significance of prime fields, specifically within the realm of cryptography, highlighting their application in the Advanced Encryption Standard, AES. A prime field, he clarifies, is a finite set of numbers possessing unique properties that make them ideal for cryptographic operations. Paar then introduces the concept of prime extensions, a method used to expand the set of numbers in a prime field, generating larger sets for more complex cryptographic computations. He emphasizes the critical role of prime extensions in advanced cryptographic applications such as AES. Further elaborating, Paar clarifies the concept of finite fields by defining them as sets of numbers in which operations like addition and multiplication are performed modulo a prime number. This means, for example, in a finite field with 256 elements, operations are performed modulo 256. This fundamental concept underscores the functioning of encryption algorithms like AES. Emphasizing their importance in cryptography, Paar underscores that finite fields are indispensable in designing robust and secure encryption systems. From 30 minutes to 35 minutes of the video, the speaker continues to expound upon the properties and applications of Galois fields, emphasizing their paramount importance in contemporary cryptographic systems. They underscore the significance of thoroughly comprehending prime fields, particularly in the domain of cryptography. The speaker then introduces the concept of field extensions, which serve as a crucial mechanism for constructing fields of greater complexity. They explain that an extension field is created by appending a primitive element to a base field. This element, denoted by the symbol alpha, plays a pivotal role in defining the behavior of a Galois field. As an illustration, the speaker presents an example of a prime field containing 4 elements, namely 0, 1, alpha, alpha, 2. Using this example, they meticulously demonstrate the fundamental arithmetic operations of addition and multiplication within the field, highlighting the unique properties of the primitive element. Notably, adding alpha to itself yields 0, while multiplying alpha by itself produces alpha, 2. From 35 minutes to 40 minutes of the video, Christof Paar delves deeper into the concept of Galois fields, emphasizing the paramount importance of comprehending prime fields within the context of the Advanced Encryption Standard, AES. He elaborates that the cardinal number of a prime field is determined by a prime number, and in the specific case of AES, this prime number is 2. The prime field containing 2 elements is represented as the set 0, 1, where all arithmetic operations are executed modulo 2. For instance, 1 plus 1 is equal to 0, and 1 times 1 is equal to 1. Paar underscores that for robust encryption, it is imperative to utilize the smallest feasible prime field, which, in the context of AES, is the field containing 2 elements. He further highlights that in AES, the field is not merely a collection of numerical values but rather a field of polynomials. Finally, he notes that prime fields find applications in a diverse array of cryptographic algorithms beyond AES, showcasing their wide-ranging applicability in securing digital communication. From 40 minutes to 45 minutes of the video, the speaker transitions from the general principles of Galois fields to their direct application within cryptography. They emphasize the paramount role of prime numbers in the construction of robust encryption algorithms, stating that finite fields, with their inherent limitations, are particularly critical for secure data transmission. The speaker elucidates the notion of field extensions, a process by which smaller fields are augmented with additional elements, thereby generating larger and more intricate fields. This expansion, they contend, is imperative for devising encryption schemes of sufficient complexity to withstand attempts at unauthorized decryption. The speaker illustrates the concept of field extensions using a simplified example, adding the element A to the field GF, 2, to construct the field GF, 2 squared. They then elaborate that the elements within a field extension can be represented using polynomials, which are subject to the rules of polynomial addition and multiplication. In essence, the speaker emphasizes that field extensions enable the manipulation of more intricate mathematical objects within a bounded set, a crucial aspect of secure cryptographic systems. From 45 minutes to 50 minutes of the video, Christof Paar elaborates on the significance of prime fields in cryptography, specifically highlighting their crucial role in the Advanced Encryption Standard, AES. He emphasizes that prime fields, characterized by a prime number of elements and forming a group under modular addition and multiplication, are indispensable for secure encryption algorithms. Paar illustrates this principle using the prime number 11. He demonstrates modular addition, showing that 7 plus 8 modulo 11 equals 4, as the remainder after dividing 15 by 11 is 4. Similarly, he illustrates modular multiplication, where 2 by 5 modulo 11 yields 10, as the remainder after dividing 10 by 11 is 10. He explains that the modular arithmetic inherent in prime fields provides a robust foundation for cryptographic operations, particularly in key generation, encryption, and decryption processes. The speaker underscores that modular arithmetic within prime fields offers a secure mechanism for data manipulation, effectively thwarting unauthorized decryption attempts by rendering the encrypted information impervious to unauthorized access. Paar concludes this segment by emphasizing the paramount importance of prime fields in cryptography, advocating for a comprehensive understanding of their properties by practitioners seeking to develop resilient and secure encryption algorithms for safeguarding sensitive data across various applications. From 50 minutes to 55 minutes of the video, Professor Paar continues his exploration of Galois fields, specifically focusing on the concept of field extensions. He underscores the crucial role of these extensions in the domain of cryptography, particularly in scenarios involving smaller prime numbers. As an illustrative example, he examines the number 2 and its cube, which equates to 8. This calculation serves as a cornerstone in comprehending the extension of Galois fields. He elaborates that extending a field entails not merely appending new elements, but rather constructing a novel field that encompasses the original elements while adhering to the fundamental principles of field arithmetic. Paar highlights the indispensable nature of these extensions in the development of robust and intricate encryption algorithms. The lecture then delves into the specific operations within this extended field, notably multiplication and addition. He elucidates the distinct nature of these operations in an extended field compared to standard arithmetic. This segment of the lecture establishes a foundation for understanding the more sophisticated operations inherent to Galois fields, which are essential for the security underpinnings of the AES algorithm. From 55 minutes to 60 minutes of the video, the speaker transitions to a discussion of backup and its significance within the context of Galois fields. He underscores the necessity of new batteries, serving as a metaphor for a renewed approach or a fresh perspective when engaging with the subject. This notion is further elucidated through the analogy of colleagues or fellow students, which underscore the collaborative nature of both learning and comprehending the material. The speaker then introduces the NV operation, which involves adding the 214 element to a number, illustrating a specific computational procedure within the Galois field. He demonstrates this process using a sequence of numerical elements 1, 2, 3, 4, 5, 6, 7, and operations such as G/T, AGEQ, polynorm, to exemplify how these elements interact and combine within the field. Finally, he emphasizes the inherent complexity of these operations and the requirement for users to grasp the polynorm concept, which is essential for navigating the intricate landscape of Galois fields. From 60 minutes to 65 minutes of the video, Christof Paar delves into the significance of grasping Galois fields for comprehending the intricate workings of the Advanced Encryption Standard, AES. He underscores the critical role of Galois fields as a specialized category of finite fields in the realm of cryptography. Paar then elucidates the fundamental operations intrinsic to Galois fields: addition and multiplication. He elucidates the concept of addition by employing a concrete example involving the elements 0 and 1. He demonstrates that 0 plus 0 is equal to 0 and 1 plus 1 is equal to 0, thereby highlighting the modular arithmetic characteristic of this field. Subsequently, he proceeds to explain multiplication, illustrating the process through the use of the same elements 0 and 1. He demonstrates that 0 times 0 is equal to 0 and 1 times 1 is equal to 1, emphasizing the inherent simplicity of this operation within the framework of Galois fields. Paar then proceeds to explicate the pivotal notion of the multiplicative inverse, a defining characteristic of Galois fields. He emphasizes that within these fields, each element, excluding 0, possesses a corresponding multiplicative inverse. He exemplifies the concept of the multiplicative inverse by demonstrating that 1 times 1 is equal to 1, thus indicating that 1 is the inverse of itself within this field. Paar clarifies that acquiring a firm grasp of these operations and the notion of multiplicative inverses is paramount for comprehending the inner workings of the AES algorithm. He elaborates on how these fundamental principles are seamlessly integrated into the AES algorithm to ensure the robustness of the encryption process. The video then progresses with the presenter further exploring the operations within a Galois field, drawing attention to their profound relevance for cryptography. He underscores the indispensable nature of comprehending these concepts, stating that they form an integral component of truly understanding the mechanics of AES. From 65 minutes to 70 minutes of the video, the speaker delves into the intricate realm of multiplication within Galois fields, emphasizing its crucial role in contemporary cryptography. They elucidate that Galois field multiplication is not simply a matter of traditional arithmetic, but rather adheres to a specific set of rules that govern the combination of elements. The speaker introduces the concept of a multiplication table as a visual representation of these rules. They illustrate this principle with the example of a Galois field containing 4 elements, 0, 1, 2, and 3, showcasing the unique multiplication table associated with this specific field. The speaker goes on to explain the fundamental concept of modulo in Galois field multiplication. When performing multiplication, the result is subjected to modulo operation, which essentially means dividing the result by a designated number, known as the characteristic of the field, and retaining the remainder. The speaker clarifies that this modulo operation ensures that the result remains within the confines of the Galois field. They further elaborate on the concept of multiplicative inverses in Galois fields. The multiplicative inverse of an element is defined as the element that, when multiplied by the original element, yields 1. This concept is crucial for certain cryptographic operations. The speaker demonstrates this concept using a Galois field with 4 elements, showing that the element 2 has a multiplicative inverse of 3. However, they emphasize that not all elements within a Galois field possess multiplicative inverses. For instance, the element 0 has no multiplicative inverse. The speaker concludes this segment by highlighting the significance of Galois field multiplication in cryptography. They state that this operation forms the bedrock of numerous cryptographic algorithms, including the widely used Advanced Encryption Standard, AES. The speaker underscores that comprehending the nuances of Galois field multiplication is essential for developing robust cryptographic algorithms that can effectively withstand sophisticated attacks. From 70 minutes to 75 minutes of the video, the speaker delves into the concept of addition within the context of Galois fields. He underscores the closure property of Galois fields, highlighting that the sum of any 2 elements within a given field will invariably yield another element within the same field. To illustrate this principle, the speaker presents a concrete example, focusing on the elements 1, 2, and 3 within the specific Galois field GF4. He systematically adds these elements, first combining 1 and 2, resulting in the element 3. Next, he adds 3 and 3, but due to the inherent properties of GF4, he clarifies that the sum of 3 and 3 is equivalent to 2. The speaker emphasizes that the addition operation in GF4 requires specific rules and yields unique results that differ from standard arithmetic. Therefore, the sum of 1 plus 2 plus 3 in GF4 is 2. This example serves as a pedagogical tool to elucidate the fundamental concept of addition within the framework of Galois fields. From 75 minutes to 80 minutes of the video, Christof Paar delves deeper into the intricacies of Galois fields, specifically focusing on the multiplication operation within these finite fields. He emphasizes the paramount importance of mastering this operation for the comprehension of cryptographic algorithms, notably the Advanced Encryption Standard, AES, which relies heavily on Galois field arithmetic for its robust security. Paar employs a pedagogical approach, elucidating the concept with a concrete example. He commences with the Galois field GF, 2 to the power of 4, which encompasses 16 distinct elements, and employs the irreducible polynomial x to the power of 4 plus x plus 1 as the basis for modular arithmetic within this field. The speaker then proceeds to demonstrate the multiplication of two elements, a and b, within GF, 2 to the power of 4. He meticulously multiplies these elements, represented as polynomials, leading to a polynomial of degree 7. He subsequently undertakes modular reduction, akin to a division operation, employing the irreducible polynomial x to the power of 4 plus x plus 1. The remainder, a polynomial of degree 3, constitutes the final multiplication result within GF, 2 to the power of 4. Through this detailed and meticulous exposition, Paar skillfully unravels the complexities of multiplication in Galois fields, providing viewers with a lucid understanding of this foundational concept and its integral role in contemporary cryptography. From 80 minutes to 85 minutes of the video, the speaker delves into the significance of prime fields and their applications within the realm of cryptography, particularly in relation to the Advanced Encryption Standard, AES. He underscores the crucial role of comprehending prime fields in achieving efficient cryptographic implementations, utilizing prime numbers as illustrative examples. The speaker elucidates that within the context of prime fields, the operation of multiplication assumes paramount importance. He then introduces the concept of modular arithmetic and provides a demonstration of its application in conjunction with prime numbers. This demonstration involves calculating the remainder after dividing a number by a prime number. The speaker emphasizes that in modular arithmetic, the remainder serves as the definitive outcome of the operation. He subsequently explains the pivotal role this concept plays in understanding the inner workings of cryptographic algorithms such as AES. From 85 minutes to 90 minutes of the video, the speaker delves into the concept of field extensions, specifically in the context of their relationship with Galois Fields and their critical role in the Advanced Encryption Standard, AES. He clarifies that a field extension involves the augmentation of an existing field by the inclusion of novel elements. This process necessitates a multiplication operation, which serves to generate a new field. To elucidate this principle, he presents an illustrative example: the addition of a new element x to a foundational field, resulting in a newly formed field comprising elements 0, 1, x, and 1 plus x. The speaker emphasizes that this is a simplified representation and does not encompass the intricate complexities inherent within field extensions. He elucidates how field extensions serve as a crucial component in AES cryptography for safeguarding sensitive information, employing the operations of addition and multiplication within the newly constructed field. From 90 minutes to 90 minutes of the video, the speaker engages in a lively and informal discussion about the concept of finite fields, specifically focusing on their relevance to the Advanced Encryption Standard, AES. The speaker highlights the AES's widespread adoption as a cryptographic standard, emphasizing its paramount importance in the realm of secure communication. The speaker introduces the notion of a finite field as a mathematical structure comprising a set of elements with well-defined operations for addition, subtraction, multiplication, and division, all performed modulo a prime number. They illustrate this concept through the example of the prime number 11, demonstrating these operations within this finite field. To illustrate the construction of extension fields, the speaker introduces an element alpha, which serves as a root of the polynomial x squared plus x plus 1 over GF, 2. This leads to the construction of the extension field GF, 2 squared, characterized by 4 distinct elements: 0, 1, alpha, and alpha plus 1. The speaker elaborates on the mechanisms of addition and multiplication within this extension field.